talking about the differences between solids, liquids, and gases. A little bit more detail than you probably learned before. Basics of it is something called the kinetic molecular theory, so that's what we're going to concentrate on. So let's get started. You guys have known all along there are three states of matter. Some of you may have known there's a fourth, and there's actually a fifth. So we'll try to talk about all of those in the context of chapter 10. All matter is made up of things that are very, very tiny and far apart. In gases, the molecules are very, very far apart. When they hit each other, they don't lose energy. There's no loss of energy because the collisions are perfectly elastic. So they go boing, boing, boing forever. They always move. They're always moving. They're unics, meaning they have no forces of attraction between them. And the temperature is proportional to how fast they're going. So when you take something's temperature, you might say, well, that's how hot it is. But really, what you're doing is you're measuring something's kinetic energy, or how fast it's moving. If we apply it to the Kelvin system starts at 0, which would be no movement. We've never been to absolute 0. We never will be to absolute 0. Think of it as this. You're in a canoe on a lake, and you take a tiny little pin and you punch, 100 holes. The water seeps through very slowly because it's a very tiny pin. But if you mop it up and take a bucket, and no matter what you do, no matter what you try to do to get rid of all the water, will there ever be a time when there's absolutely no water in the canoe? Of course not. We can get very, very close to absolute 0, but there will never be a point where we actually reach absolute 0. We've been to a couple millionths of a degree from absolute 0, but always some heat is leaking in from the outside, and so it's a system where there will always be a little bit of heat. For our purposes, we don't usually worry about that, but we can measure the temperature in Kelvin and know that the particle movement is proportional to that. So if the temperature goes from 200 Kelvin to 400 Kelvin, we know the particles are going twice as fast. So that's the basic idea behind the kinetic molecular theory of gases. All of those would also be true, except for the first one and the fourth one for solids and liquids, because they do show forces of attraction and they tend to be closer together. But for an ideal gas, we're going to make these assumptions, and it helps us understand why gases are what they are. So what's the difference between a real gas and an ideal gas? You can make any gas ideal because real gases have forces of attraction, and real gases take up space. And it's really hard sometimes to calculate the effect of how much forces of attractions matter and how much the fact that gas molecules take up space has. And so what do? We just ignore it. That's why we call them ideal gases. But in the real world, we know that gases do take up room and that they actually do show forces of attraction. But we can take any gas and make it ideal by getting it very, very low pressure, which means there's very few gas molecules. That means they're super far apart, and make them go really, really fast at a high temperature. Because if you're going super, super fast and there's hardly any other molecules around you, you can't have forces of attraction that really matter. That's why your parents want to keep you busy, keep you away from other people. There will be no forces of attraction. I like to think of my children as being ideal children. There are no forces of attraction. Just the way I want to live. You don't want to think about your parents making out and that kind of thing. Same way. We can take any gas and make it ideal. We're going to assume all gases are ideal gases like me. Let's see if you know the difference. What's compressible? Gas, solid, liquid. What's compressible? You can compress a gas, right? You cannot compress a liquid. You cannot compress a solid. Which one has the highest density? In other words, which one would sink? We're not counting ice. There's always some smart aleck out there. So which one has the highest density? Solids have the highest density. Gases have the least density. Which ones are fluids? Well, what is a fluid? Fluids are things that flow. So what flows? Gases and liquids, correct. So solids don't flow. Gases and liquids do flow. Fluids flow. Which ones diffuse? All of them diffuse. Although gases tend to diffuse the easiest and the fastest. Bonding. Which ones have the strongest bonds between them? I call this the run through it test. Which one's easiest to run through, a solid, liquid, or a gas? Gas, because it has the least bonding between it. Okay, there's a couple different kinds of solids out there. There's amorphous and crystalline. Amorphous, it means it doesn't have a whole lot of structure to it. Crystalline structures are structures that have a whole lot of protein in them and no fat. No, not really. That's crystalline. No. Crystalline means that it has a regular repeating structure. Amorphous means a very random structure. Crystalline means a regular repeating structure. Those words right there, you don't need to know them. So if you see them in your book, don't worry about them. Those are things that you will encounter later in college or somewhere like that. You don't need to know them now. You need to be able to do this. What is an example of a crystalline solid, like salt? What's an example of an amorphous solid, like plastic or asphalt? And then can you tell me the difference between ionic crystalline solids, covalent network solids, and so on? Okay, so just make sure you know what each one is and an example of each one. All right, I did promise you 2 other states of matter. The 4th state of matter is called a plasma. Plasmas have to do with heating up matter so hot that the electrons not just jump up and jump back, but they jump clear off. So a plasma is nothing more than an element or a compound in which it's been superheated and the electrons are flying off. So really, it's an ionized gas, right? That's what a plasma is, an ionized gas. If you'd like to see one of those, you can look inside of fluorescent light. You can look in a candle flame. You can look at the area around the sun. Those are all good examples of plasmas. They conduct electricity, which is one of the reasons why scientists like to use them. The last one is called a Bose-Einstein condensate. And a Bose-Einstein condensate is named after Bose and Einstein. Very good. And what they did was they postulated the idea that at super cold temperatures, so close to absolute zero, that matter will behave differently. And this gets super freaky. So if you were way into physics and you like this kind of freaky stuff, you might want to look it up and see what's going on. But a Bose-Einstein condensate talks about when matter gets super cold, it behaves differently. So imagine a cup full of water. When it's super cold, assuming it doesn't make ice, so you got to play along with me here. Imagine putting a little bit of water in a cup, and instead of sitting at the bottom, the water actually crawls up the sides and forms an even layer up the sides and across the bottom. Matter behaves differently when it's super cold because there are different interactions between them. They're not moving very fast, so the bonding is different. And this was postulated by Bose and Einstein very early in the 1900s, and then later on it was proven to be true. And that's actually in the last, I think, 10 years, we've actually proven the existence of the Bose-Einstein condensate. So 5 states of matter. We'll actually play with this some in class. So when I see y'all in class tomorrow, we'll play with some PhET simulations that let y'all look at matter and how it reacts.